Question 3 involves a car, and there's no like crazy loop-de-loops in this question. It's just a car going over a hill. And in a situation like this, we say that the hill traces a circle whose radius is 50 meters. So what I've drawn in this picture is like this green dotted line is supposed to represent the circle that the car kind of traces, the profile of the top of the hill traces it, and it's 50 meters in its radius is 50 meters. So the car itself is traveling 30 kilometers an hour. We should immediately see kilometers an hour and think, oh God, better convert that to meters per second. So 30 kilometers per hour is equal to 8.33 meters per second. And for those of you that want to see the conversion, it's like this. It's 30, and then we're going to multiply that by something, 30, and it's kilometers on the top. I want to get rid of kilometers, so I'll put meters. The conversion here is 1,000 meters in 1 kilometer. Then I'm going to multiply it by, now it's hours on the denominator, so hours goes on the top. In 1 hour, we've got 3,600 seconds. So that will give me, if I multiply, so 30 times 1,000 divided by 3,600 is 8.33. My units cancel, and I am left with, let me just write it like this actually, 30 kilometers per hour. So now I can see that my units will cancel. My kilometers cancels, my hours cancel, and I'm left with meters per second. So this car is traveling at 8.33 meters per second. The question asks the normal force exerted by the road on the car. So if we draw a free body diagram here, this car is traveling in a circle. It obviously has a force of gravity because it always does. It also has a normal force because the road is supporting it. But because it's traveling in a circle at a constant speed, we can say that it's accelerating towards the center of the circle. It's accelerating at that instant. I've drawn it. It's accelerating down. So in that case, if the acceleration is down, that means the net force is down. That means what we're saying here is that Fg, or let me put it this way, Fn has to be smaller than Fg, so that there's a net force pointing downward. You can kind of feel this when you go over if you take a hill. If anyone who's ever been to PV, there's some crazy roads and they just they look exactly like this. They go up and down. And when you fly over the top of those roads, you feel like your stomach bottom out a bit. And that's because your normal force is changing. It's becoming smaller because of this simulated circular motion. So if the acceleration is down, remember what we said in the last problem, we're going to take down to be positive and up to be negative. So now we're just going to solve this like we solve all of our problems. And then I'll do that right here. So this is part A. Actually, I'll start it right here. So what we're saying is Fc equals the sum of the forces, which equals mv squared over r. Now in this example, the sum of the forces, now keeping track of the signs, since down is positive, Fg is positive. So we've got Fg minus Fn. Fn is up, which in my diagram is negative. And that equals mv squared over r. The question is asking us to solve for the normal force. So we can see that rearranging this equation, we get Fn is Fg minus mv squared over r. All right, so then let's solve this. So Fn equals, this is 975 times 9.8 minus, just move this over, minus m, which is 975, v squared, 8.3 squared, 33 squared, divided by 50. So let's solve this out each piece at a time. So 975 times 9.8 is 9,555 minus, and then that term times divided by 50, 1,354, 1,354.2, I guess you could say 0.2 newtons. So then subtracting that, we get 8,200 newtons. So I want to just unpack this a little bit. If this car was just like, when this car, I should say, is driving over here, just like on a flat road, before it gets to that hill, we know that it's level, so FG is going to equal FN, right? These two are going to be equal to each other. So in this example, if FG is equal to 9,555 newtons, then the normal force is also going to be 9,555 newtons. So the car has a normal force of 9,555, but when it goes over this hill, that number drops to 8,200. So the normal force drops, and that's because it's almost like, think of it like the ground is sort of falling away, and it's not it doesn't need to support the weight, the full weight of the car, because the car is sort of trying to fly forward. The car is trying to move in this direction, but the ground is curving beneath it. So the normal force will decrease appropriately. And the amount the normal force decreases really depends on the speed you're going. As you can see from this term here, the faster you're going, the less your normal force is going to be, right? It's going to get smaller and smaller the faster you're going. So that's kind of one of the things that happens, is your normal force decreases. Now, how about the actual driver of the car? How does his normal force change, or her normal force change? So for part B, you've got the seat, right? Let's say this is the seat of the car, and then you've got the driver sitting in the seat, driving the car. So in this case, it's the same question, it's just with a smaller mass. There's the force of gravity, and there's a normal force. But remember, this guy is accelerating down because he's kind of going around this circle, right? And that circle is, even though he's not turning upside down, it's still creating a circle. So that's making the gravitational force greater than the normal force. So in this case, we do the same thing. Fc equals sum of the forces equals mv squared over r. Same forces. We've got, again, we're going to make down positive and up negative because of the sign convention according to the acceleration. So we've got mg minus fn equals mv squared over r. Now the person is traveling the same speed as the car. So the normal force, same equation, is Fg minus mv squared over r. So now we can just put that in, 62 kilograms times 9.8 minus 62 times 8.33 squared divided by 50. So let me solve that. 62 times 9.8, and that equals 607. 607, and then the other term is 62 times divided by 50, and then so subtract 86.1, and we get 607.6 minus 521.5. 521.5 newtons. So again, the person feels lighter. The normal force is 607 newtons, but the person feels like they're only 521 newtons. And so that's kind of why those big hills sort of make you feel like, your stomach bottoms out a little. And that's because of this reduction in your normal force. And now the question says the speed at which the normal force of the driver equals 0. So you can imagine a scenario where the normal force gets smaller and smaller and smaller until the point at which it goes to 0. So then the only force acting on you, here, let me copy this whole diagram, and then we'll put it down here. Can I do it like this? No, insert. Okay, so here's this diagram, and we're going to put it over here. So here's the diagram. All right, so this is it for part C. But what we're saying now is this car is just flying so fast that the normal force is dropped to 0. So the question is, how fast would you have to be going for that to happen? And in that case, we do the same thing. Fc equals sum of the forces equals mv squared over r. Now the only force is mg. So mg equals mv squared over r. Doesn't matter whether we're talking about the car or the person. The speed is going to equal the square root of g times r. You saw this in the previous problem. It's the same idea. And now 9.8 times 50, take the square root of, so the square root of 49. The square root of 49 equals 7. Well, I could have done that in my head. Oh, no, it's not 49. Sorry. It's v equals the square root of 9.8 times 50. Oh, that's what I was thinking. V equals 50 times 9.8. It's 490. Square root of that is 22.1. So that's a lot faster. Just for reference, this is 3.6. So this is 79, let's say 80 kilometers an hour. Kilometers per hour. Per hour. So in the first part of the problem, you were doing this lovely like 8 meters per second or 30 kilometers an hour over this hill, and you felt this, this little sensation in your tummy as your normal force decreased. If you now go take this hill at 80 kilometers an hour, you're just going to fly. And basically what's happening is you're going so fast, it's like you're kind of coming off the... Yeah, I'll come in. I'm finishing a video. All right, my son needs me. So hope that makes sense.